Well, here I am once again talking to myself. This is class 2, section 2.2, statics, particles for statics. And of course, that makes sense, right? Statics, yeah. We're adding forces by components. The bottom line up front, as I like to try to begin classes after going over the previous homework, the idea is that we have a vector. We could break it down into its x component and its y component. And if we're going to add it with a second vector, we break that one down too. And then the resultant that we're going to get when we add them together is found by adding those components together. And we end up with the resultant. So that was the bottom line up front. And we're going to start working through there. All right, well, let's take a step back and think about what a force looks like if you break it down into components. We have a magnitude and a direction for the force vector. As with all vectors, we have a magnitude and direction. And quite often we will have a Cartesian coordinate system, x and y, named after Descartes. I think, therefore I am, the same dude. And within x component and the y component, we like to break down these forces into them. There's nothing that says that the axis has to be aligned with horizontal and vertical. We can pick a coordinate system that is convenient for us for a number of reasons. It doesn't. It might be because whatever we're working on, the reference just is convenient for us. It could be like something on a slope or something along those lines, and so we can break that x and y down. So we should be kind of comfortable with that. The idea of a unit vector is that very word, a unit, right? That means that its magnitude is equal to 1. Right, of a unit vector, and they're aligned with your x and your y coordinate here, and we write them by hand by putting a caret on top. That little guy right there, to show that they're vectors, because a lot of times they'll use bold in the book, but we can't do that. But we are a unit vector. So really what these do is they just establish a direction, and I just point out things to come. Unit vectors, they don't necessarily have to be this Cartesian. They could be other types of coordinate systems that might be useful in whatever application that we have. So when we write out a vector, it will look like that component as a magnitude. So that component, like in y, is just multiplied by that j. And we notice that with the angle, which is pretty standard quite often, not always, but quite often it'll be measured counterclockwise from horizontal. We have to be kind of flexible in that, because they in the book they do put angles in all different kinds of places, so we have to kind of think our way through. But in this orientation right here, we'll be taking the sine of theta times the magnitude of the force right here in order to get the component, and then we multiply it by j. And the same thing for the x direction. We would take that the magnitude of the overall force, multiply it by the cosine of theta, and that would give us fx. So if we were going to write this out, the equation that represents this vector right here, we would write it as fx, and I like to put things in parentheses just to kind of snug them up together, is going to be fx times I hat plus fy times j hat. And usually you should put units like right after that. You could also have said that it's going to be f times the cosine of theta I plus f times the sine of theta j. And I'm just being completely thorough. We don't necessarily have to do that every time, but it's good to completely write these things out. So we have concept applications. So these are actually examples. So I'm going to end the lecture right here. Maybe not. Let's see, how long are we going here? I'll sneak a peek. We'll discard what we've written so far, and the lecture is only 5 minutes long, so I'm going to keep on going. I like to try to stick with 10-minute lectures if at all possible when recording things. So in the concept application, let me escape out of this. I'm going to fix this later on. It would really help, I think, to give myself some more space when I go to teach this. So I'm going to move these up here out of the way. And these are like little concept applications are like the little mini examples. I think they're doing these because we want to make sure that we could feel like what the usefulness of it is, because so far it's just sort of an arbitrary thing, a force that we're breaking down. Well, let's imagine an application where we have 800 newtons in tension of rope that's attached to a stake in the ground, and we want to know how is that broken down into the vertical and the horizontal components. Well, we set up a coordinate system. It's convenient to be horizontal, so that's good. And then we take a look and we write the thing out. So if we were going to write out the fx component of that, you notice that they provided the 35 degrees, but this time it's going to be clockwise from horizontal. Well, let's be flexible with that. And when we're writing out the fx, let's go ahead and make it negative, because it is in the negative x direction, and it's 800. And then we will use the cosine of the 35 degrees. And we're left with negative 655.3 newtons. Now, the book rounds down to 3 sig figs, and I have instructed you to not. So we will not be following through with what the book says. We will be doing it the way Dr. Deal has instructed us, because I don't know why they're being silly. Because they left off that 0.3, and it's an in-between step, so we're not going to do that. Let's just speak to the publisher. And the Fy, we want to take a look at the vertical direction, see how much of it is, and that's going to be the sine of 35 degrees. And you get 458.9. The book rounds to 459. Naughty, naughty. And so if we're going to write out what the vector is here fully, I like to put the negative sign inside a parentheses. And this is going to be my final answer, and I give you the flexibility for a final answer to be 3 to 4 sig figs, so you can go ahead and not round down, just leave it like there, but I want it boxed, right? So there is a complete answer. In the concept application 2, we have this little dude, and he is pulling on this rope, and we happen to just know the geometry of it, and we also know, we were also given that he's pulling at 300 newtons, right? So what we want to do is we want to find the force vector. It turns out you can't push a rope, right? You ever heard that phrase? Hopefully I'm not the first person to tell you this, but you can't push a rope, but so the orientation of the force has to match up with the orientation of the geometry. So the force has to be in the direction that we're showing right here. So we're able to figure out what that geometry is. And if we're going to look at alpha, because it's a convenient thing to look at right here, we would find that by taking the inverse tangent. And we always tend to think of rise over run or getting opposite over adjacent either way. In this case, it's going to be 6 divided by 8, right? Because 6 is opposite from your alpha right here. I don't like to use alpha because that's actually angular acceleration sometimes. But anyway, we get 36.87, and that might, for some of you, become a familiar angle that might turn out. So let's take a pause and think and look at this. What do we see? 6 and 8. Does that ring any bells? Do you recall the 3, 4, 5 triangle? Triangle. Well, yes. So we have 6, which is 2 times 3, and we have 8, which is 2 times 4. So we know the length of that rope is 10 based on the 3, 4, 5 triangle. We can also find magnitudes by taking the ratios of these things, and that's what they've done in the book. I personally like this. It just makes me feel comfortable to go ahead and find these things using the angle a lot of times. But in this situation, you could do it either way. So like if I was going to use the angle for this to find fx, I would say, well, fx I know is to the right, so it's positive, and it's the magnitude this. And based on the angles that I see, that it's going to be the cosine of my 36.87. That you could just as easily find this by taking the ratio. Let's see, I could take the ratio of this should be, let me see, I got to do this in my head, 300, and that's going to be 8/10, right, of the thing. If you took the cosine of 36.87, you should find out that it's 0.8. And so we get 240 newtons. And that's going to be positive, so it's to the right. And Fy, we'll say that it's negative because we know it's downwards, right? And then sine of 36.87. Or we could have written that as 300, and that's going to be ratio of 6/10 of the thing, which we would have got in a calculator anyway. Oh, I should have carried that negative over there. So, and by the way, sometimes it's like we might, the book or someplace might want to draw an arrow. Something I caution you at is to never, see, it doesn't matter up here, but don't put the arrow on something that has a negative. Rewrite the thing out if you're trying to express it with an arrow, because the arrow and the negative sign is like a double negative. So if we were going to write out what this force is, we would say that it's 240.0 I plus a negative 180.0 J newtons. And that's the complete answer. And then lastly, in the concept applications, let's see, someone is calling me from Cornwell Bridge, Connecticut. They probably want my insurance or something. No, that's my warranty, right? So in this problem right here, we're given components. We want to find magnitudes. Just want to make sure we can go back and forth. So the given, if you will, is that the force is equal to 700 I plus 1500 J newtons, and we want to find F and theta. So to do that, I want theta first for some reason. We could take the inverse tangent of rise over run, right? So that would be Fy over Fx, or inverse tangent of 1500. I'll put parentheses around that one too. And then 700, and we would get 64.98. Now the book rounds down to 65. I don't like that. That's not good engineering practice. So we want to find the magnitude. We know that it's the square root of the sum of the squares of the thing, or 700 squared plus 1500 squared, and that equals to 1,655 pounds. And the book wanted to note that you could also, so we have an or, you could find that magnitude by taking Fy and dividing it by the sine of theta. So you could, if you just take 1500 and divide it by the sine of 64.98, you end up with 1,655 pounds. So you get the same thing, right? So we might want to give a complete answer, rewrite the thing out, and theta is equal to 64.98 degrees, and box it in. So that right there would be the complete solution. How long is our thing last? We have a 14-minute. So I think maybe I will break off right here, and we'll say done.